And the next speaker before the coffee break is Federico Vincentelli, who is gonna present us everything on fast infrared variability for new MAXI black hole transients.
Hi, do you hear me?
Yes, perfectly.
Okay. Do you see my slides? Do you see the presentation?
Yes, perfect.
Okay. So hi everyone, I'm Federico Vincentelli. I just started a postdoc with Joy Nielsen at Villanova University. So it's 3 o'clock in the morning, so I apologize if I don't speak, I don't do a perfect speech. Today we'll present you results about fast infrared variability, so sub-second resolution about the 3 transients that we talk about this week, 1348, 1535, and 1820. So while, as we discussed a lot this week, X-rays and radio emission are well identified, but we are still, let's say, struggling with the details of the structure. Optical infrared emission is not really fully understood, the origin, because we have 2 main scenarios. So the first scenario is more, I would say, the more historical one, that we think during the hard state that there is, we interpret this break that we observe as a success as the optically thin emission from the jet, so before the break. But there's also another interpretation that can manage to explain in the hard and intermediate state the infrared and optical emission as synchrotron radiation from the hot inflow. So given that we have this double interpretation, understanding studying this optical infrared fast variability, especially correlated with the X-rays, can be very constraining. And so to do this, so we do this kind of observations. We measure the correlated variability, and we can measure mainly 2 things: the cross correlation function that gives us information about delays between X-ray and optical and infrared, but we can also see, for example, anti-correlations or complex CCF. And these are 3 examples of 3 different sources, and we already can see that they have very different shapes. And CCFs also evolve as a function of time. So this tells us that there are at least 2 components or more are at play. At the same time, we can, when we have simultaneous observations, we can do time lags in the Fourier domain, as Tom explained a few days ago. But we can also just study the amplitude of the power spectrum, and this allowed us to detect the optical and infrared QPOs. And for example, in this case that I'm showing here for 39-4, we were also able to we were also able to track the QPO as a function of time. So this also can be very constraining because, as you could see, this follows the X-rays. So the models that managed to explain this wide phenomenology are, as I said, the 2 main models of variability is one for the jet and one for the hot inflow. And these 2 models have main characteristics to explain the variability, and they have particular strengths and particular features that I want to stress here. And this is, of course, my humble opinion, and maybe it's not absolute. It's not an absolute. So internal shock model for the jet explains the optical and infrared fast variability as shells that collide inside the jet. And this presents a natural explanation for the 0.1 second lag that we observe in certain CCFs, because it's the location where the shock happened. At the same time, the hot inflow model explains very well the more complex CCF with a very natural and, let's say, I would say almost elegant way, because it assumes that the synchrotron radiation comes, the optical is emitted from the synchrotron radiation, and the X-rays is self-synchrotron content from the same population of electrons. So it is, the anti-correlation is embedded in the model. And then if you just assume that there is let's say a reasonable assumption that there is reprocessing, then you can create this anti-symmetric cross-correlation functions. Moreover, the hot inflow has quantitative predictions for the optical and infrared QPO lags, while for the internal shock model and for the jet in general, we don't have quantitative predictions, but we can still do some qualitative modeling. So I'll go directly to the data. I'm sorry that I'm skipping a lot of details, but we can discuss them later. I don't have a lot of time, unfortunately. So MAXI 1535 is so was observed through SmartNet at different wavelengths, near, mid-infrared, and X-ray simultaneous. This is the first, I think, example at this high time resolution. I will focus mainly on the X-ray and the near-infrared part, and in particular on the Fourier domain techniques that we applied. As you can see, we detect for the first time a QPO in X-ray and infrared at the same frequency. QPOs were not detected in infrared at the same frequency before. And as you can see, the observation was at high, the QPO is very high, around 2 hertz, so close to the transition. And we can see that there is a 0 phase lag at the QPO. This is the first time that is seen at infrared wavelengths. And as I said before, hot inflow allows us to put constraints on this component, because it from the modeling and preliminary modeling showed that if the infrared QPO is arising from the infrared, these are the parameters. In particular, I want to stress that the inclination has to be higher than 50 degrees, and the radius has to be 30-50 Rg, so a bit big to be close to transition, but the inclination is consistent with what we see with X-ray spectral measurement. At the same time, something I found very interesting is that if we assume that the infrared comes from the jet, the scenario changes completely. So if we just assume a causal connection between X-ray and infrared component, and we put an upper limit through the phase lag of 0, we get actually the opposite. So the inclination at this point has to be lower than 40 degrees, so inconsistent with what we find with the inflow, and the gamma has to be higher than 1.7. But at the same time, this inclination is consistent with what we find with radio measurement. So we have a dichotomy between the two inclinations, and to me it's very interesting and very intriguing. To me it might be seen that there is some kind of misalignment at place, but I'm happy to discuss about it later. 1820, the black hole of the week, the star, everybody just the most cited black hole of the last months. We did a campaign in 2018 and also in 2019, but I'm presenting here mainly the result of 2019 during the soft state, the transition from soft to hard state that is still poorly studied. I want to just show you very quickly an example of a light curve during the hard state. This is, as you can see, in 2-3 minutes, it's very, very variable in the infrared. The CCF that we obtained is consistent with what John Pace found, and this result was also part of the campaign by Alex Titarenko, where she managed to constrain very well the jet variability from optical infrared to radio and submillimeter. And just I want to show you this CCF because we will see now that the things change dramatically when we go from soft to hard state, in the transition from soft to hard state. So this is a light curve that we get, a light curve that a collaborator, Meta Basbey-Arabachi, is about to publish in a paper of the soft to hard transition. There is a gamma, and when we observed, we have a gamma of around 2, and we can see that the radio rebalancing started, but the infrared and optical rebalancing did not start yet. So this is quite and other observations this state were already further on for G6 and it's very interesting that when we go and see the CCF, the CCF is actually inverted. So the CCF is so at this point the infrared is leading the X-rays, and this is actually the first time that this is seen clearly. And so while we usually see, for example, for jets that there is a lag of the infrared is lagging 0.1 seconds, here we see the opposite. And actually there is no clear model which manages to explain this scenario. So I think, like I was thinking about self-cyclotron component in the jet, I think this the lag is around 0.1 sec. Sorry?
3 minutes
3
left.
minutes. Okay, yes. So it's around 0.1 seconds, 0.2 seconds. So this is certainly too big. I wanted just to say that there is this striking similarity with the CCF and phase lag that in this the paper by Sasha, where she compares soft and X-ray lags and tries to explain it as two components in the soft and X-ray band and hard band. So this we are now working together to try to see how to apply this model to this data. And very quickly, I want to show that actually this is not the first. It's not really the first time that we see it, because John Pace in the transition from hard to soft, it's like around first days of June. You can see that in this observation there is the rising of a component at negative infrared lags. So again, we see the infrared hint of infrared lead. And also very quickly, there is the student Alberto Luggiati, who worked with Pier Giorgio Rosella last year on his master thesis, and seems to find from archival Swift J7053 observations an infrared lag, a negative lag. So this lag is becoming more and more often, and so it will be important to understand it to constrain the jet, the accretion flow. Last thing, last source, very quickly, 1348. We know that there was a NICER monitored this source very intensively and managed to detect transient QPO features. We did a very intense campaign, as also Poshak showed this morning, with the SmartNet campaign. This is an example of how unlucky observations can be. We did not manage to get, even though we used SmartNet, and for the other observations we did use SmartNet and were successful. In this case, we did not get strictly simultaneous observations, but only quasi-simultaneous observations. But this is part of the game. However, at the same time, we managed to detect a type B QPO in the infrared, and this is actually the first time that this is detected. And so I'm very curious to, now that there are also more new models to try to explain the X-ray QPO properties like RMS and lags, how this result will help to constrain these models and understand the nature of type B, so that's still very uncertain. So this is the summary, and I just take questions from here. Thank you very much.
Thank you. Are there any questions? I see someone in the room.
Thank you. There is this last object that you talked about. You said that you have infrared QPO detected. Do you have almost simultaneously X-ray QPO observed also at the same frequency?
It's more or less the same frequency. As you can see, the QPO is we don't get strictly simultaneous observations with the X-rays, but it is in the same range where the other QPO was detected. Yes.
Okay, but you don't have simultaneous, so that's why you cannot get the lags. Yeah.
No, but you can probably compare the RMS, I would say.
Phil, online?
Yeah, thanks. For the infrared lead in MAXI 1820, do you have the Fourier resolved phase lags?
Here it is. It's the one there.
Just the, okay, right. So it's, you can sort of see the time scale. So that positive lag is an X-ray lag, is it?
Yeah.
Okay, right. So it's like a second time scales. Yeah.
Yes.
Okay. Yeah, no, thanks. Yeah, it's kind of interesting you have that dip in the middle as well. So yeah, okay, curious. Because of course this 1820 has these quite strong negative lags at, frequencies above 1 Hertz, right? For example, in Jingyi Wang's talk and Erin Kara's 2019 paper. But not, I don't know about this state because this is a bit later on than those observations.
Yeah. Yeah. So you mean it might be related to the soft reverberation lag?
I mean, no, but I mean, with NICER data, you always have to be careful as well when you're doing that comparison. But this isn't NICER, right? This is XMM. Yeah, so I guess similar band though. Okay, yeah, I'd have to think.
I tried to check the energy dependence, and there was not like a strong dependence between soft, like 0.15 to 2 kV, and above that. There was not a big difference in the phase lag.
Okay, thanks.
Great. Do we have?
Yes, a question from Alexandra Veledina.
Okay.
Hi, Federico. Thanks for the nice talk. So my question is about the difference between the rising phase and the decaying phase. It's not maybe not a question, but a question to the discussion. So we seem to see there is a difference between the optical and infrared behavior, how it behaves or how it compares to the X-ray band in the rising phase and as compared to the decay phase. Have you ever, do you have any thoughts about that?
So so there are two things here to keep in mind. First thing, the gamma of this observation, so the spectrum is very hard in this observation and also in the one by John Pace. And the other thing I think that's probably most important is that we are, I'll put full screen so you can see it better. We are in a state that actually is never observed, have never been observed so far with these kind of observations. So it is before the infrared rebrightening. What we observed with JST-10-4, where we saw something like similar to what we find in normal hard state, was after the infrared rebrightening. So I think this is why we are seeing something different. So we are in the canonical hard state, but we are in a regime that is still like close to the transition, I would say, but the other way around, because we are from soft to hard. But if anyone has other comments on that.
Okay, I think we can thank Federico again